we are going to do is we're going to maintain, instead of using the automaton to keep track of which are the longest two prefixes, we are going to explicitly remember every prefix, okay, at runtime. Okay, so that's one idea. And the way we do this is, let's look at a picture and it's easier to understand. Let's say we put a token on each of these states, okay? And the token kind of remembers whether you have a match going up to that state. Okay, so we might put a token in, you'll always have a token in the first state because you're always willing to start a match. And then depending upon how far you have gone, you might have tokens in some of the states. So for instance, if you take our running example and you are in this position, right? Then you have tokens, right? So if you maybe I don't have that much space. Okay, so that is the automaton, so you can assume all the symbols, right? So A, B, so and if you are here, right, then you have a match for the empty prefix, so there will be a token over there. There is a match for a prefix of length 1, so there will be a token over there. And then there is a match for a prefix of length 4, so there will be a token over here, right? So we are going to maintain all these tokens at runtime, okay? And then we will advance all these tokens at runtime. Okay, this is the basic idea. And of course, if we just do it naively, it's kind of stupid, right? Why does one want to spend, that much time? So the way we are going to be clever is by not representing these tokens, by using a bit vector to represent all these tokens. Right? So if you have n states, then we are going to use a bit vector of length n to represent whether a token is there in each of these states. Right? So it's a Boolean quantity, right? So the token is either there, which again, token being there means you have a viable match up to that point. So you have a viable match of length 0, viable match of length 2, length 1, and viable match of length 4 at this point, right? So the presence of token says what are the viable matches you have, and we're going to use a bit vector to represent what are all the viable matches, okay? And the point is to try to do all the matching operations by doing one operation or a constant number of operations on the bit vector, okay? And then if the bit vector itself is going to fit in, let's say, 1 or 2 words of memory, right, then you can do those operations in constant time, right? So if it's going to require 200 words, well, it wouldn't make sense to think of it as a constant time operation, right? At least in a practical sense. But you can see that if you're talking about a keyword search problem, right, your word size these days is 64 bits, right? So, well, keywords longer than 64 can occur, but at least you can see that keywords less than 64 are probably occurring frequently enough that it will be useful to have an algorithm that can work on them. So again, this algorithm is useful when the length of the keyword that you're searching for is small enough that it's going to fit in a small number of words, right? 1 or 2. Okay? So the way we are going to do is we are going to maintain these tokens, and then each time we see a symbol, we are going to advance the tokens, right? And then otherwise they die. Okay, so let's say over here, right? So we see a B. Okay, so now we want to go from over there. So if you see a B, well, this token can advance, right? So we are going to advance this token. Okay? Now, this token can advance too, right? No, it can't advance, I'm sorry. So this token can advance because it's a B, right? So this token cannot advance because it's not a B, right? So this token basically dies. And this token also cannot move over here, right? But there will always be a token at state 0 to say, okay, we always have a match for prefix of length 0, right? So that there's always a match for the empty string. So when you see the next symbol, one token is able to go forward, all other tokens die out. Okay. In some cases, multiple tokens can go forward, right? So how will we know that? Well, we basically any state from which the outgoing transition, or rather the next symbol, right, matches the input symbol, you are going to be able to go forward. You are going to be able to advance the token, right? Otherwise, you cannot advance. So let's see how we can represent all of this using bit vectors and so on. Okay. So. Okay, so we are going to represent the match state using a bit vector called t. Okay, t0, the 0th bit of t represents whether there's a token in the first state, and then so on, right? So that's what we're going to do. We're going to represent the state of these, the presence of these tokens using a simple bit vector. Okay, now. That is a very intuitive concept. Now the next thing we need to do is to say how to advance these tokens in a constant time operation, right? All of these tokens are to be advanced in one operation, or else the whole thing doesn't make any sense, right? So how do we do that? So we do that using another bit vector that tells us from which states you have a forward transition on each character. So for instance, there is a transition on A from states 0, 1, 3, 6, and 7. Right? So some of these states have transition on A, and what we are going to do is we are going to use a bit vector to represent which states have a transition on A. Okay? And we are going to call that as delta A. Okay? There is of course going to be a delta B, which says which of the states can advance on D. Okay? So now to understand how this is set up, keep in mind that bit vectors, we have a convention of labeling them from right to left. Right? So we write down right? So this is what we will call as bit 0, and this is what we will call as bit 7, right? So this is the convention that we generally use for labeling bit vectors, okay? Of course, the states, we label them left to right, right? So this is a right to left labeling, and then that's a left to right, okay? So that has to be kept in mind, and of course I could have said, okay, let's change it around and label the bit vector from left to right, but you'll see the next slide that labeling bit vector from right to left actually is convenient because it makes it easier to explain what's going on. Okay, so let's understand why is this, right? What this means is that state 0 can advance on on A, right? Because this is delta A. Okay, so what this says is that state 0, the match can advance on A. State 1, again, look at the automaton, right? You'll see that from state 1, you can advance on an A, right? And state 2, you have a B. So obviously, you cannot advance a match for A on state 2. That's why there's a 0. And then the next state, state 3, has a transition on A, therefore this will be 1. So essentially, what you have done is you look at the automaton, right? Delete everything that's a B, or rather replace everything that's an A with a 1, replace everything that's a B with a 0, and then because of the ordering difference, just flip everything around. Okay, so that's how you get delta A, right? So same way you do that for B, and you'll see that, okay, again, the delta B, right? So you see, okay, the first two positions don't have a match, so 0, 0. Then there's 1, right? And then there's 0, because the next position is an A, and then we have a 1. Did I get this? Let me see what I got. 0, 0, 1, 0, 1, right? And then 0, 0. Okay. So this is always going to be 0. Okay, that's fine. Okay, so that says which position, which tokens can advance on B. Okay, and then all I need to do is, if T represents my current match, right? Advancing the token is nothing but shifting this left by 1, right? So I want to shift everything to the right, and because the bit vector I'm labeling them in the other direction, instead of shifting to the right, I'm going to shift to the left. Okay, so this is what I'm doing, and of course I'm masking it with the corresponding delta. What that tells me is that I'm going to only advance, make the shift for those bits where I have a match between the next symbol, right? So this is the next symbol, right? So S of K is the next symbol that I'm going to look at, and what I'm saying is that if there's a forward transition on that symbol, only those things are going to move forward. So let's look at this again in the picture. Okay, so we have a S and you have a P, right? So the way to remember this is that this is the state of the match so far. What this means is that you go straight up to S, right? And what this one tells you is that a match starting at the position is still viable. Okay? So you can see that this one starts with A, B, which is a prefix A, B, right? So it goes straight up there. You see A, B, and that's the prefix of this. That means you still have that can advance. Correct? Okay? So then you want to advance the match based on seeing the next symbol. So we set K equal to 11, and that's pointing to that A, and we want to see how to advance the match. Okay, so what we do is we say we're going to do the operation that we did in the previous slide, which is you're going to mask T with delta and then shift it to the left by 1. Okay, so what we do, we mask 1, 1. This becomes so the new position, right? We said the token, there will always be a token in the 0th state, so you can just ignore that. So this is going to flow into this provided these two are 1, right? So we are going to take, because we are taking a bitwise AND of these two, right? And then if that ends up being 1, then that will be shifted to the left, or rather, because I already put this shifted to the right, they just flow down, right? So 1, 1, 1, and 0, 1 is going to become 0. And so anywhere where both T and D have a 1, you're going to have that thing. Yeah?
Ignore the 0th state there, the 0th state of this.
Keep in mind that 0, the bit vectors always have 0 on the rightmost, right? This is bit 0. Right? Otherwise, okay, that's all. That's why it's a shift left and not shift right. Okay? Okay? So, again, because I've laid them out in this way, the way the ANDing and shifting ends up being basically checking whether these two are both 1, and then if they are 1, you put a 1 here, otherwise you put a 0. Okay, so it becomes a very simple, at least pictorially, it becomes very simple to see what happens. Okay, at least to visualize what happens. So now, let's go through the next step. In the next step, what I'm going to do is I'm going to take this T mu, and move it over there, okay? Or rather move it over there, right? Because I have to align the T with the corresponding place in S. So I'm just going to move this over there, right? And of course, when I go to the next slide, a few things will change over and you won't be sure exactly what I've done, but that's exactly what I've done, right? So the T new from the last slide has become T, and you can see these two ones and this one's there. And we again apply the same thing. So these two are one, so, and then, right? So at this point, right, you have a 1 here, which basically means that you have a token in the 8th state, right? And whenever you have a token in the 8th state, it means you have completed the match, right? So anytime you see the nth bit of T becoming 1, you can announce a match. Okay. So like in the other case, when we are doing regular expression matching, whenever we see the dollar position appearing, then we call that a final state. Same way, here we do this. Okay? And there are a few more steps, but I don't think that necessarily adds to anything. Okay, it's just useful. You can look at it over there. Okay? Now, the reason why we talked about this algorithm is because there are reasons why we talk about this algorithm, and there is one reason maybe why we shouldn't talk about the algorithm, and that is there is no easy way to generalize this algorithm to deal with multiple patterns. Okay, because bit vectors are one-dimensional, right? So I can advance the match for a single string, but if I have multiple strings, you think about it, that the match is like a front on a tree, right? And so how can I advance in all those positions if all I have is a single bit vector? So in general, I have no way of extending this algorithm to do multi-pattern matching, okay? But I can extend it in a different way, and that is for doing approximate match, okay? So all the finite state automaton techniques are only good for exact match, right? They cannot be used for approximate match. The approximate match algorithm that we talked about is one that's quite expensive, right? It's got order of nm complexity, right? Which is whereas here we are generally asking for algorithms that are order of n. Okay, we can't do that. But this particular bit shift algorithm is amenable to support approximate matching with same complexity. Right? Basically, in order of m time, that is, where m is the size of the string in which you are searching for these patterns. In that time, in linear time, you can find that. So how do we do that? We use what is called a Levenshtein automaton. So what does Levenshtein automaton do? It's basically an automaton that allows certain error transitions. Okay, so the error transitions are basically capture approximate match means you can have some mismatches, right? So those mismatches will be explicitly captured as transitions in the automaton, and that's what we call as Levenshtein automaton. So exactly what happens here now, this is the simplest case where no errors are permitted, right? So it's basically exact matching automaton. Okay, so now let's say I want to allow one character to be missing. So then that is my automaton, right? So I have, I can either go forward, if I see an A, I can go forward to the state, or I can say, maybe I may be missing that state, that A, so I will just make an epsilon transition over here, right? So you can see that U is, the U chain is just a copy of T chain, right? And the only reason why I have it is because I want to remember that I already, deleted one character. So I don't want to say, if I put an epsilon transition from T0 to T1, then I won't remember how many characters I have missed, right? So I want to remember because the algorithm that I seek here is one which tells me all the matches that are within a certain distance. Okay, we aren't trying to compute the minimum edit distance here, right? Because that's not the problem. The problem is there an approximate match for this keyword inside this text, right? So you just have to say yes or no. So in order to make that a distant problem, you need to say, okay, within a certain edit distance, right? Or with at most, you know, 2 insertions or deletions, or 3 insertions or deletions. Okay, so that's how you formulate the problem. And so the automaton has to remember how many errors you have made, and for that purpose, we are going to basically have multiple chains, each chain corresponding to one error level, right? So the T chain corresponds to error of 0, U chain corresponds to error of 1. Okay. And right now we just have we are accepting deletions, right? So some characters could be missing. Okay, we are not able to accept insertions in this automaton, right? But we can do that. So how can we accept insertions in the? How can we extend this to accept insertions? Well, you could never go from U to T because we said U says one error of 1, right? So you can't go from U to T.
And if you add one more, like U, we need to add one more.
You don't need to add any more states. So let's make the question a little bit more structured. You don't need to add any more states.
From T1 we need to go to U0.
On what? On what symbol? To tell me what the transition is, what you should tell me what the symbol on the transition is. I mean, it's not a wrong answer. I'm just wanting you to be more specific. Any other answers? How can we accept insertions? Right? We want to say that, let's say we want to allow either one insertion or one deletion. Okay? We don't want anything more than that. One insertion or one deletion. Then how can I modify this automaton to allow one insertion?
You can go from T2 to U1.
T2 to U1. On what? Again, what is the symbol of the transition?
The character which is
A.
Not A. Because if you go on A, then you're actually inserting 2 characters, right? So because you go from T0 to T1 on A, and then you're going from T1 to U0 on an A, so you've eaten up 2 characters, and you're still in them at the beginning, right? So basically, the answer is almost right. Right? All you need to do is to go from T0 to U0, T1 to U1, and so on. Okay? And the other aspect is that the transition character doesn't match because you don't care what is being inserted, right? So you can have a transition on any character in. So that is the automaton, right? So I use sigma to say any character in the alphabet can be consumed, and so you go up. Any questions? This is clear, right? So now how do we do, now we have done insertions and deletions. How do we do substitutions? So will this automaton allow any substitution?
Transition for insertion and substitution, they would be the same thing. Like the transition for insertion and substitution, they would be the same.
No, right? Insertion is increasing the length of the string. Substitution doesn't, right?
We need to add a new set of states instead of epsilon, we need to put the.
Again, you don't need more states.
You can go from T1 to U2. T1 to U2.
T1 to U2 on
Reverse the.
on sigma once again, right? So that's what we do. Okay. So now we have an epsilon transition which says you delete, basically don't have to have anything, or a sigma transition which says you can see anything and go forward, right? Now, again, the way we have drawn this, we still are making sure that whenever you are in the U chain, you have a distance of 1, and whenever you are in the T chain, you are at a distance of 0. So now, suppose I want to allow distance of 2, then what do I do?
We have to go from T0 to T0 to T0 to C2 and T1 to U3.
So one suggestion is that we introduce, instead of going from T0 to U1, we allow T0 to U2. Is that going to work? Is that going to work? What will be the problem? So there is a problem. You can't just go 2 steps forward and that's not solving the problem. And then why is it not solving the problem? It is definitely allowing 2 insertions or 2 deletions or whatever. Okay, so you're getting. Okay, I would rephrase it as follows: when you do that transformation, then you're requiring the 2 insertions and deletions to occur together, right? I want one insertion to occur here and another to occur there. I need to be able to separate that. So how do I do that? That's what I do, right? I just create another stage, right? And again, we have to have our mental picture clear, right? The chain represents a distance. So we try to do something funny which destroys that semantics, then we are not going to succeed, right? Because if we put these transitions forward, across 2 states and so on, then the meaning is no longer that we have a distance of 1. Now we are saying the distance could be 1 or 2, and then of course we can never, recover from that. Right? Once we don't know what the distance is, the atometer is not going to help us. So we just stack one more stage, and now we say distance of 2 means you'll be in the V chain. Okay, and then you're done. Okay, so we know how to construct this automaton. So we sort of at least have an intuitive idea of how to do approximate matching. Right? So this is a non-deterministic automaton, right? Because it has epsilon transitions. So it is a non-deterministic automaton. Not only because of that, but also because you have an A transition and you have a sigma transition. Right? So that's another reason why it's non-deterministic. Right? Sigma is anything. Right? So as a result, this is a non-deterministic automaton. So one way to use this automaton is to construct the transform it into a DFA, which of course will make it large, right? So if you don't want to do that, so the other alternative is to directly simulate the NFA, which we talked about. You just say, okay, the NFA could be in one of the 21 or 24 states, and you're going to see where can it go on the next symbol, right? So you can do either of those. Those are the standard techniques, but neither one is particularly attractive. One is potentially very expensive in terms of storage, the automaton size. Another one is potentially very expensive in terms of the. Okay, so what are we going to do? We're instead going to take the bitmask technique and extend it for this problem. Okay, and what we are going to do is very simple. Right, so intuitively the picture is clear. To go forward, right? So we need. So now we have several chains, right? So we basically are going to have one bit mask for each chain. Okay, and that way we are going to be, if there are k chains, then we'll have k bit vector operations. But otherwise everything will be found. Okay, and now what we need to do is, previously we only worried about operations where you're going within a chain, right? So now we have to support operations for going, all these. So only these transitions, right, were previously supported in that algorithm. Now we have to say how to support this transition, that transition, and this transition. Okay, and we are going to do that. So how do we do this? Well, first of all, we need to slightly refine our notation. So what we are going to do is we are going to put T is still our bit mask, right? T is our bit mask that represents the tokens in the T chain. Okay, there will be U bit mask for the tokens in the U chain and so on. But we are also attaching a superscript K to tell us that we are where we are in the string that we are matching on S, right? So remember in the algorithm we were at a position K in the subject S, right? So that K is going to be explicitly represented because otherwise it will be difficult to see what's going on. Okay? So, and this is the same formula as before, right? Previously we said, okay, we are going to T new was T, bit and with this delta and shifted to the left by 1. This was the formula we had before. It's exactly the same formula except that we are also noticing that, okay, we were at position K minus 1 on the subject string, now we are at position K. Right? So instead of calling it T and T new, we are calling it TK minus 1 and TK. Okay, that's the only change so far. Okay, so now how do we go to U? Okay, so what we're going to do is we're going to say UK is TK minus 1. Okay, and this is basically the move up. Right, so what we are saying here is TK minus 1, we are at position K minus 1. Okay, so this is UK, which means that we have forwarded one more position. Okay, and what we are saying, because that transition up is on sigma, which means it doesn't matter what the character at the kth position is. That's why there are no bit masking things going on here. TK minus 1 can simply go to UK. Okay, and then you can also see pictorially that T0 goes to U0. Okay, that's kind of what's going on here. Okay, so all of these tokens are basically able to go up, right? All the tokens from the T row can go up to the U row when there is an insertion, correct? And that's yet another way to think about this. Okay, so that's one transition going to the U row, and there are two more, right? There are two diagonal transitions, and we need to capture those. Okay, and then finally there is a forward transition of the U's themselves. Okay, so this is the upward transition, and this is the right transition. Okay, this right transition is again the one that we already seen, right? You just do the delta masking and shift to the left. So the U tokens are going forward. So that is this one. Okay, and T tokens are just shifted up to U. That is this one. Okay, so now you have the two diagonal arrows. Okay, the two diagonal arrows means you are basically shifting T0 to U1, right? So that's why you have a shift by one operation going on here. Okay, and you can see that both of those arrows are okay. So one of them is on sigma, right? Which means that you're going to consume one character. So that's why you go from TK minus 1 to UK on that transition. Okay. The other one is epsilon transition, which means that you are not consuming anything. That's why you're going from TK to UK. Okay. But the tokens are always advancing, right? So they're always going cross. So the tokens in both cases have to be shifted to the left by 1, right? Because they are advancing. But the superscript has to be advanced only in the case where you are matching against sigma, because that says you have matched one more character from S. Whereas in the case where you are doing epsilon transition, you haven't taken anything from the string, and so you go from TK to UK. Okay, and you can see once again we are back to the familiar picture with horizontal moves, vertical moves, and cross moves, and so on that we saw in the edit distance algorithm. Okay, and so. So you can see that, okay, so I can compute the U matrix, the U bit vector in a constant number of operations, right? So if I have L stages, then I will need only order of L operations to compute all the bit masks. So in order to do approximate string matching with up to a distance of L, well, I'll do order of L times M. Okay, so that's let's basically stop there, and we will